And then the promise of quantum computing, the present landscape of quantum computing, the challenges. And actually what is interesting, we are no longer talking just quantum computing, but quantum technologies. A large number, those of you who are kind of abreast, you must have seen there's a list of technologies floating around, which came from the World Economic Forum. What are the 10 technologies of 2030, etc.? And quantum sensors is one of the technologies. So it's not only quantum computing, but quantum technologies as well. I don't want to leave you without giving you some basics of what quantum mechanics is. So we'll talk about key concepts in quantum mechanics and then about getting quantum ready. And of course, as I said, the purpose of this is not to teach you quantum physics or quantum mechanics or quantum computing or quantum technologies, but to give you an idea as to why this is an interesting and important thing to learn. It is not only purely interesting from its cognitive challenges or mental challenges, but also in terms of if you're looking for jobs and careers and so on, these are the best careers which are waiting for you. I will share with you that as of date, the only place which offers a engineering degree in quantum technologies is University of New South Wales, Australia. US is now working very hard to quickly develop curricula for quantum technologies. And let me get you a flashback in terms of tech engineering programs. Now, the earliest engineering branch that we know of was civil engineering. And that was one of the earliest. And I won't go right now into why it was called civil engineering and not construction engineering. And then we had mechanical and electrical and electronics and textile and chemical and computer and all these kind of things started developing. So this is what is very important to realize. And many of these come out of basic things from physics. So let me kind of, all of you have heard of Faraday's experiment. So Michael Faraday, before Faraday's experiment, people looked at electricity and magnetism as two separate things. So magnetism was seen in magnetic bars and poles and so on and so forth. Electricity was seen in batteries and sometimes it was static electricity. Faraday did a very interesting experiment. What Michael Faraday did was that he took a wire, connected it to a galvanometer, and then waved a magnet in front of the wire. And as he waved the magnet in front of the wire, there was a current in the wire which could be detected by the galvanometer. This many of you have heard of as Faraday's experiment and so on and so forth. So the first one to bring the connectivity between electricity and magnetism, and so that after that we actually use the word electromagnetism and we use electromagnetic waves and so on and so forth. So it's a very interesting story. So when he was demonstrating this in the Royal Institute Hall, etc., in London, the Chancellor of the Exchequer, he came and he said, but what is the use of it? And Michael Faraday is reported to have said that, sir, one day you will be able to put a tax on it. And this is, today electricity units are all, there's a tax on top of that, the GST, etc., and so on. And electricity is sold for a price. And sometimes even elections can be won if you have the right policy, what electricity prices. So this is what happens. So we begin with something which is a pure curiosity of scientists. You do some experiments to demonstrate that. And then, as you know, people like Edison created the electric bulb and created this whole wiring thing and General Electric Company and so on and so forth. And electricity was not limited to lighting bulbs. We had various aspects of electricity which could be used to create heaters, to make refrigerators, to make motors, to make generators, various kind of things. This is where it becomes into technologies. And the same thing is happening for quantum mechanics. It began with certain theoretical ideas, which of course I will share with you. But today there are practical applications coming out of it. And that is why we are talking of quantum technologies as almost a new branch of engineering, if you want. And it is requiring, so just like an electrical engineer is different from a mechanical engineer, is different from a chemical engineer or a civil engineer, a quantum engineer or a quantum technologies engineer will be different from either of these. And today and tomorrow, he is the most valued person. So anyway, let's go to the next slide. So what I'm talking here is just the kind of thing we drove for quantum mechanics. And that's why we've labeled it pre-quantum mysteries. So what is it? So why was, let us say, quantum physics or quantum mechanics needed? And this is the, I put up some four things which are important to raise. So I mentioned to you that electric bulb had come and Edison and Tesla and all these people were doing this company. So one of the things, so you know that if you heat something, it emits light, and I think you are sophisticated enough that I can use it, emits radiation. Now, whether it is a piece of coal, a piece of glass, wire, or anything, if it is heated, it can be a simple piece of metal. You heat it, it will start glowing, and we say red hot or white hot or whatever. This is the thing which was called black body radiation in some sense. So the big challenge was that when you heat something, as you heat it, it emits largely red light or something of that kind. This was well understood. The problem was that if they looked at it that way, if you made a lower temperature, it should have emitted blue light or ultraviolet light, but that doesn't happen. And if that were so, we would all be surrounded by ultraviolet radiation, and there would have been what is called an ultraviolet catastrophe. So the challenge was, one, why this is happening. So people could explain the higher part was all right. You heat it, it becomes red light, it is fine. But then why does it not become blue light when it is colder? The other thing was that, as I said, when the bulbs started coming and people realized that there's an electric bulb and it emits all kinds of radiation, from a commercial point of view, they wanted to have a bulb where the visible light would have been highest. Because they're not interested in the other light or heat or etc., which is being wasted, and they wanted more and more of visible light to be there. So these are the two things which inspired the understanding of black body radiation. One was pure scientific curiosity and the anomaly as to why does it happen. The other was that if we know how the radiation is dependent upon temperature, we will be able to create better light bulbs which give more light in the visible region. And this is where the first one to have made something into quantum mechanics, Max Planck, he postulated something. And he postulated that the radiation is dependent, the energy of kind of a particle of that is dependent upon the wavelength or the frequency. Now, it is very interesting, and I'll share this because this unlike many other fields, quantum mechanics did not come by a single, so not like the Faraday thing or the Newton's law or any other such thing that suddenly one person one day decides to make a certain law. It's actually a whole thing about 20 years or so. And so when very often, even the people who are promoting this are not agreeing, not only not agreeing with others, they are not even sure of themselves. So when Max Planck did all this and explained the radiation, he said, but I don't understand this. I don't quite believe it. It gives me the right answer, but I don't know why, etc. type. So this is a very interesting kind of thing. The other thing that happened was the atomic spectra. So when you see lines coming from a certain thing, the spectrum, those lines are of very specific frequencies. For example, you know, the halogen lamp that you see has largely yellow light. The mercury lamp has blue light. The neon lamp has red light. So why does this happen? The basic thing that was happening was the same. And this is where atomic spectra became an important thing to drive towards, so why should this happen? Another thing was that as we understood the atom structure of the atom, and we knew there was a nucleus and there's an electron, and the electron moved around the nucleus. This was the Rutherford model of the atom. But the problem was that if that electron is moving around the proton or the nucleus, it would emit radiation, because the moving electron will emit radiation and therefore it will lose energy and therefore it will collapse. So it would not have been stable. And this is where Niels Bohr came up with a theory that it is true it won't be stable, but if it is in certain places at certain frequencies, and which is where quantum words started coming in, this could be stable. Again, he has no idea why, what, but he says if we assume this, then we are able to explain a stable atom, and we are also able to explain the atomic spectra of various things. And finally, Einstein observed the photoelectric effect. Not only observed, he explained the photoelectric effect. And he also, to explain that, had to assume some quantum thing to the energy of the various photons that were there. So these are some of the things which were driving, and it did not happen in an instant. It took 15, 20 years of various people exploring various aspects of nature, all of which seem to require a set of assumptions, which people came across different. As I said, they did not agree with each other sometimes, they did not even agree with themselves. But as these things explained more and more of nature, it became acceptable.